Hello everyone, my name is Jung Kim, and I, along with my fellow colleagues Max Majuri and Lucas Smallage, are proud members of I Can't Believe It's Not Water. Today we shall be discussing a seemingly simple yet difficult task, the extraction of colored dye from water. So today we will be talking about several aspects, including our objectives and process throughout this project. So without further ado, let's get started. So before we get into more depth, it's important to understand what we want to take away from this project. So there are two major objectives we'd like to achieve, one being a relatively high flow rate, and two being a large amount of purification. But we have to understand that there's a trade-off between these two aspects, so we ultimately want to be in the middle of this diagram. So in other words, we want to use as much filter materials as possible to ensure the cleanest water, but not so much so that the water filters out at an efficient rate. In addition to our main focus, we considered several secondary elements throughout this project. First, we believe that a filtration device should be more than just a pipe with materials inside of it, right? So with that said, we decided to have it resemble something relatable, such as a NASA space shuttle. We also thought about enhancing our photometer by integrating it as a filter device and allowing the LED to change colors automatically. And doing so would account for greater convenience and flexibility for our device. And lastly, we limit ourselves to one medium, and by succeeding in this, we would be able to save materials and money while having a functional filter.
Our first iteration was the result of insufficient materials. While we had planned to use an end cap to hold our filter media in the housing, there was a shortage, and we resorted to using saran wrap with a slit cut in it. The rock and sand were chosen to keep the carbon in the bottom of the filter and aid in the slowing of the flow rate. Overall, this filter iteration proved to be the most effective of the three, most likely due to the extended amount of time the dye water spends in the activated carbon. This is due to both the relatively small hole cut in the saran wrap and the slowing of the flow due to the sand. This iteration was an attempt to diverge from our original ideas in the pursuit of making the simplest, least expensive filter possible with our materials. This filter performed most poorly out of the three iterations, exemplified by both its low flow rate and low dye removal. This, we concluded, is due to the fact that the dye water spent very little time in the activated carbon, but saturated and clung to the cheesecloth, where it slowly dripped down into the collection container, barely filtered. This final iteration included all of the stretch goals we set out to meet at the start of the project, namely the multicolor spectrophotometer with a flow-through design. One ambition of ours was to include a syringe in our design in an effort to automate the process. Our plans to use a syringe were quickly thwarted, however, when we saw how difficult it was to control the flow rate of the system. Our original goals proved to be the downfall of our design, as the tubing size was selected due to its compatibility with a syringe, and when used without a syringe, the inner diameter proved to be too great. This large inner diameter increased the flow rate to a detrimental level, as the dye water had little chance to interact with the activated carbon before it was drained from the filter. The housing is placed within two styrofoam cups, which provide a base and the ability for the hose to be inserted into the bottom of the housing. This also provided us with the opportunity to design the filter after a NASA space shuttle, earning us an aesthetics stretch goal. The spectrophotometer is placed in a custom-made cardboard housing, which is designed to block out ambient lighting, improving the accuracy of the spectrophotometer.
In the trade-off between high flow rate and high dye removal, the flow rate was king. The flow rate was extremely high, and because of this, we weren't quite able to get the dye removal we were looking for. However, we were still able to remove a whopping 1.43% of dye in the 7 seconds it took for the 10 milliliters of contaminated water to flow through the filter.
Now, for the sake of curiosity, let's take a look at the cost breakdown. So, as shown in this table right here, each row displays an item, how much was used, and its total cost. So by determining all such, and after adding up the individual costs, we determined that one device would cost $229.36. So this accounts for not only supplies we ordered, but also tools that we used throughout this project, like scissors and spray paint.
Aside from the required elements, performing at least one design iteration, creating a filter that could accurately measure dye removal and flow rate, and making a monocolored spectrophotometer using Arduino, we were able to complete 4 additional stretch elements. The rocket-themed filter was very aesthetically pleasing. The multicolored spectrophotometer allowed online monitoring of the dye water every half second by incorporating a tube that could pass between the LED and the light sensor. Also, we decided to only use one type of media, activated charcoal within the filter. Because the flow rate of our filter was so high, the water didn't have much time to come in contact with the media. To combat this problem, one possible improvement would be to replace our current housing with a taller and thinner housing. This change would decrease the area the contaminated water has available to flow through, causing it to come in contact with more media over a longer period of time. In effect, more water will be filtered. Another idea would be to mix different types of media together. Depending on whether the media would be finer or larger, we could expect a higher or lower flow rate, which would give us an additional tool to control the flow rate.